Give it a twang. And so we got a really slow natural frequency here, got a really fast one, and we got one in the middle.
In this test, the Tacoma Narrows natural frequency is most similar to the slow one. When winds hit a bridge, they create mini whirlwinds, called vortices. The problems start when these vortices have the same natural frequency as the bridge. This is called resonance.
If I now start to shape this support for these three bridges, if I do it really slowly, just give it a little motion, at the natural frequency of my big slow one, you can see that the big slow one really starts to respond, and we get massive amplification. And the other two are hardly doing anything. If I do it at intermediate sort of speed, the middle one goes wild and the other two stop. And if I go really fast, just the little one goes wild and the other two stop.
On that morning, with vortices created at the natural frequency of Galloping Gertie, it was only a matter of time before resonance caused the bridge's collapse. Tacoma terrified bridge engineers. Suddenly, wind was the enemy. They went back to the drawing board and discovered that the way to combat resonance was to bolt extra beams underneath the deck, called a stiffening truss. At vast expense, bridges around the world, including the Golden Gate, were retrofitted. It seemed the stiffening truss was the only way forward. That was until the late 1950s, when a young British designer came up with a new idea. And after countless awards, more than 40 years later, Bill Brown still plays down his role.
I think I was probably at the right place at the right time, in fact.
The magic of Bill's idea was to work with the wind rather than against it.
I didn't know that it would work aerodynamically. I knew it would work structurally, but not whether the aerodynamics would work.
Bill came up with the idea of reshaping the deck of the suspension bridge to make it aerodynamic. The wind is deflected around it, and the deck flies in the wind. Bill had just finished the Forth Road Bridge and had won the commission to build a crossing over the River Severn. This would be the first bridge in the world to have this new deck. But first, he had to test it. 40 years later, Bill demonstrates what his wind tunnel tests showed. First up, he tests the Tacoma deck.
You can see the Tacoma Narrows section is twisting quite violently.
At just 40 miles per hour, the Tacoma deck cannot withstand the wind.
We now have mounted the Severn cross-section, and we're running this now at 150 miles an hour. As you can see, it is absolutely stable. This is because we have an aerodynamic section, the wind is flowing above and below it, streamlined, and the forces are low.
The Severn Suspension Bridge was opened in 1966 and would lead the way in modern bridges.
The magic is that it is streamlined, and therefore the wind forces are low, and there are very few vortices. So generally speaking, we don't need to add structural resistance to overcome the wind forces.
After the success of the Severn,